In this video, we're going to look at another type of infinite series known as a telescoping series. The question here is to evaluate the following series. We have summation, k goes from 1 to infinity, 1 divided by k times k plus 2. Part B, summation k goes from 1 to infinity, log of k plus 2 divided by k. Our strategy in both questions is to find a formula for the partial sum Sn and use the partial sum to evaluate the series. So we'll take the limit as n goes to infinity of Sn to see if we can find a finite sum, to see whether the infinite series converges to a sum or whether it diverges. So let's begin by writing Sn, looking at the nth partial sum for part A. So we have Sn is equal to k is equal to 1 to n, 1 over k times k plus 2. Now plug k equals 1, we get 1 over 1 times 3. Plug k equals 2, we get 1 over 2 times 4. Plug k equals 3, we get 1 over 3 times 5. And the last term, k equals n, we get 1 over n times n plus 2. All right, we're going to apply partial fraction decomposition so we can obtain a closed form for the partial sum Sn. So we have 1 divided by k times k plus 2. We have a product of linear factors, so we write this as a divided by k plus b divided by k plus 2. We take common denominator, which is k times k plus 2. So in the numerator, we get a times k plus 2, adding these two fractions, plus b times k. This is equal to, let's simplify this, we get a plus b times k plus 2a divided by k times k plus 2. Now let's multiply both sides by k times k plus 2 to clear out the fractions. We want to get rid of these denominators. So on the left-hand side, we just get 1. On the right-hand side, we get a plus b times k plus 2a. Let's rewrite this so we can equate coefficients and solve for the unknown a and b. On the left-hand side, we can rewrite this as 1 plus 0k. On the right-hand side, we can write it as 2a plus a plus b times k. Now looking at a constant in the left-hand side, we have 1 is equal to, and a constant on the right-hand side, that's 2a. So 1 equals 2a. We're equating coefficients. Constant on the left-hand side has to be equal to the constant on the right-hand side. Solving for a, we get a is equal to 1/2. Now, the coefficient of k on the right-hand side has to be equal to the coefficient of k on the left-hand side. So we get 0 is equal to a plus b. Solving for b, we get b is equal to minus a. And a we solved for it earlier, that's 1/2, so we get b is equal to negative 1/2. So 1 over k times k plus 2. We applied partial fraction decomposition. We can write this as 1/2 divided by k plus negative 1/2 divided by k plus 2. So the nth partial sum can be written as Sn is equal to k equals 1 to n, 1 over k times k plus 2, and we applied partial fraction decomposition to write it in a different form. K equals 1 to n, 1/2 divided by k plus negative 1/2 divided by k plus 2. All right, so we have Sn, the nth partial sum, is equal to 1/2 summation, k goes from 1 to n, 1/2 divided by k, minus 1/2 divided by k plus 2. 1/2 is a constant. It passes through the summation. We can factor it out, so we get 1/2 times summation. K goes from 1 to n, 1 divided by k, minus 1 divided by k plus 2. Now Sn is equal to 1/2 times Plug in k equals 1, we get 1 over 1 minus 1 over 3. Plug in k equals 2, we get 1 over 2 minus 1 over 4. That's the second term. Plug in k equals 3, we get 1 over 3 minus 1 over 5. That's the third pair, I guess. I should say the pair. And plug in k equals n, we get 1 over n minus 1 over n plus 2. Now let's expand this. We get Sn is equal to 1/2 times 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus 1 over 4 minus 1 over 6. Now let's plug in n minus 3. So k equals n minus 3. That's 1 over n minus 3 minus 1 over n minus 3 plus 2 is going to give us n minus 1. Now plug in k equals n minus 2. So we get 1 over n minus 2 minus 1 over n minus 2 plus 2. That gives us n. Now plug in k equals n minus 1. We get 1 over n minus 1 minus 1 over n minus 1 plus 2. That's n plus 1. And lastly, plug in k equals n. We get 1 over n minus 1 over n plus 2. And now we look for cancellations. So 1/3 cancels with 1/3. Negative 1/4 cancels with plus 1/4. Negative 1 over n minus 1 cancels with 1 over n minus 1. 1 over n cancels with negative 1 over n. So notice that on the left-hand side, we have 1 remains, and the first term remains, and the third term. So we mirror that on the right-hand side. So you can see the first and third terms remain from the left side, the left end of this equation, I should say, and the last term, negative 1 over n plus 2, remains, and the third last term also remains. So we get negative 1 over n plus 1. This is a closed form for the partial sum that can be evaluated as n goes to infinity. That was the goal of applying partial fraction decomposition, so we can write it pairwise and start seeing these cancellations and getting a closed form and simplifying the partial sum so we can evaluate it. All right, so notice that the telescoping nature of this infinite series, with almost all of the interior terms of the sum canceling out, we're left with a simple formula for Sn. That simple formula is Sn is equal to 1/2, 1 plus 1/2, minus 1 over n plus 1, minus 1 over n plus 2. So the summation, k goes from 1 to infinity, 1 divided by k times k plus 2, this is equal to the limit of the partial sum Sn, limit of Sn as n goes to infinity. This is equal to limit n goes to infinity, 1/2 times 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. Let's take the limit. The limit as n goes to infinity of Sn is equal to 1/2 times 1 plus 1/2, because 1 over n plus 1 will approach 0 as n goes to infinity. Similarly, negative 1 divided by n plus 2 approaches 0 as n goes to infinity, because the denominator in both cases, n plus 1 and n plus 2, they grow infinitely large and the ratio becomes 0 as n goes to infinity. If we simplify this, we get 1/2 times 3 over 2, and the result is 3/4. So we write this as the given series, is a telescopic series, the given series, that's the name for it, telescopic series, converges with sum is equal to 3/4. So we can write summation k goes from 1 to infinity 1 over k times k plus 2. This infinite series has a finite sum. It converges to a sum, and that sum is 3/4. Now let's look at another type of telescoping series. Here we have Sn is equal to log of k plus 2 divided by k. Let's apply the rules of logs and rewrite this in a different form to see the cancellations. N equals 1 to infinity log of k plus 2 minus log of k. Let's put that in brackets. So Sn, the nth partial sum, is equal to, plug in n equals 1. Sorry, this should be k. Plug in k equals 1, and this upper limit should be n, because we're looking at the nth partial sum. So Sn is equal to log of 3 minus log of 1 plus, plug in k equals 2, we get log of 4 minus log of 2, plug k equals, we plugged in k equals 1, k equals 2, k equals 3, that's log of 5, minus log of 3, and plug in k equals 4, we get log of 6, minus log of 4, and so on. So now let's plug in n minus 3 for k, so k equals n minus 3, and we get log of n minus 3 plus 2 is n minus 1, minus log of n minus 3 plus, and now let's plug in n minus 2, so n minus 2 plus 2 that gives us n, so we get log of n minus log of n minus 2. Now plug in k equals n minus 1, we get log of n minus 1 plus 2 is n plus 1, minus plug in k equals n minus 1, log of n minus 1, and plug in k equals n, we get plus log of n plus 2, minus log of n. So now we're going to get some cancellations. So log 3 cancels with minus log 3, log 4 cancels with minus log 4, log 1 of course is 0, and we have log n cancels with minus log n. We have minus log of n minus 1 cancels with log of n minus 1. So when we simplify this, we get Sn is equal to minus log 1 minus log 2. Notice that the second term and the fourth term on the left side survive, so we mirror that on the right end. So that means that the second term here, minus log of n plus 2, that's going to survive, and the fourth term from the end, 1, 2, 3, 4, log of n plus 1, that also survives. So we get plus log of n plus 1. So it's mirrored on the other side, log of n plus 1, plus, but you have to be quite strategic in terms of writing out quite a few terms of the series to get all of these cancellations to happen. So that's why we had we went up from k equals 1 to k equals 4, I guess, and on the other side we started with k equals n minus 3, k equals n minus 2, k equals n minus 1, and k equals n to get all these cancellations. So we can get a simple form for the nth partial sum, so we can evaluate it as n goes to infinity. Sn is equal to minus log 1, that's just 0, minus log 2. So let's just write this as minus log 2 plus log of n plus 1 times n plus 2. We can do this simplification using the log rule for multiplication. So now let's take the limit as n goes to infinity of Sn. This is equal to limit as n goes to infinity of minus log 2 plus log of n plus 1 times n plus 2. Now clearly this limit is going to be infinity because log x is an increasing function of x. So log of n plus 1 times n plus 2 will go to infinity as n goes to infinity. And minus log 2 is just a small number. That's like minus 0.693. So in any case, the limit as n goes to infinity of the nth partial sum is going to go to infinity. That means the series diverges to infinity. That means summation, k goes from 1 to infinity, log of k plus 2 divided by k. This telescoping series, this infinite series, diverges. It diverges to infinity. It has no finite sum. This infinite series diverges to infinity. All right, thanks.